Hi everybody, welcome back. Chapter 6, Forces. We've talked about two of Newton's laws already. That is Newton's first law, that is the law of inertia. Objects that rest stay at rest, objects in motion stay in motion. And we've also spoken about Newton's second law, which is the famous F equals ma, force equals mass times acceleration. Now we're on to Newton's third law, which is, it should be familiar to many of you as well. People oftentimes call it the action-reaction law. That is, take, for example, with respect to rocket ships. If you've got a rocket ship and at the bottom of the rocket ship you've got gases that are expelled in that direction, creating a force in that direction, there is an equal force applied to the rocket by the gases as well, propelling it forward as well. So for every force that is applied to an object, there's an equal but also opposite. So equal in magnitude, opposite in direction force that is also applied to that as well. Forces never occur in signals. They always occur in pairs. So the way we notate this is as such, down at the bottom right here. So we'll say two objects, object A, all right, and object B. All right, the force, let's say object A applies a force onto object B. All right, so say your object A, okay, this is you, and there's a tabletop, all right? You apply a force down onto the table with some sort of a magnitude. The table also applies a force back to you. Table and you. Okay, with the same amount of force. You can't push on the table without feeling the same force from the table on your hand as well. The only difference, the magnitude is the same, but the only difference is that it is opposite. So whatever force is applied from object A to object B, it is equal to the negative of the magnitude of the force. That is, you can think of it as B applying it to A right here. So in the next example, there's going to be a canoe example. We're going to look at that very thing and apply this. So here's our example 6.5. And we've got canoeists. Now the reason we use canoeists is because canoeing involves being in water, and water is a relatively frictionless surface on which to float. Of course, you probably know there is friction in water, but we're going to pretend that there isn't. Okay, and so we've got canoe 1 right here. We've got canoe 2 right here. And so canoe 1 applies a force onto canoe 2. So we're going to call it that right there, all right? So the way we're going to notate this is the force of, I should make that a capital F, just because. Force from 1 to 2, all right, is, what is the value of that force right here? Well, it's 46 newtons, we're told, okay? 46 newtons. But this guy, if you look at this guy right here putting his hand on the canoe, he can't apply a force to canoe 2 without also feeling the same magnitude of the force pushing it back on him as well. All right, so we're going to call this force 2 to 1. All right, if we look at that, if we look at our axis right here, here's a positive x-axis, here's negative x. So this would be the negative x direction, so it would be negative 46 newtons that 2 is applying to 1 right there. So I'm not really using the notation that they're giving us right here. I'm calling this force 2 to 1 right here, and this is force 1 to 2. I think that'll help us to keep things a little bit more organized, okay? So with that in mind, we now have two masses. We've got this canoe right here. It has less people in it. What is it? Canoe 1 has 150 kilograms worth of people in it. That's the mass. And canoe 2 has a different mass. That's 250 kilograms. All right. We've got a force on each canoe. Force 1 applied to 2, and force 2 applied to 1, which is in the negative direction. And we have a mass for each. So it should be fairly easy to find the acceleration for each canoe. All right. Different masses, but the same force, just in opposite directions. Also, Part B asks us, what is the separation of the canoes after 1.2 seconds of pushing? All right, well, I'll address that when we get to it, all right? But that really is asking us, what is the delta x of both canoes? All right, that is how far apart are they after he has applied that force for 1.2 seconds. All right, so let's go to the next slide right here, and I'll kind of write this out, and we'll start solving it. All right, so Canoe 1. All right, so A asks us, what is the acceleration of Canoe 1? A1 equals question mark, A2 equals question mark. Right? You know, I had been writing A1 in green, but I'm not going to keep changing colors right now. This is the first one in green, but I'm going to stay in red. All right. So always write down everything we know about each canoe. So Canoe 1, the mass of that canoe. Let's see. I'm going to write it out horizontally here. Mass of Canoe 1 is 150 kilograms, and the force applied to Canoe 1 is, what did we say it was? Well, it's the exact same force, it's the exact same magnitude of the force that Canoe 1 applies to Canoe 2, just in the opposite direction. So we said it was negative 46 newtons. All right. Well, what's the, how about Canoe 2 right here? All right, so Canoe 2. By the way, you know, I'm going to sketch this out. I'm going to draw my canoe right here. So here's Canoe 1 with the two guys in it. All right, I don't know what that is right there. But Canoe 1 is receiving a force of negative 46 newtons. My drawing is really starting to get kind of horrible here. 46 newtons, there we go. All right, in Canoe 2, let's write everything we know about Canoe 2. Canoe 2 has more people in it, so it's going to have greater mass. So the mass of Canoe 2 is 250 kilograms worth of mass. The force applied to it, we call it force 1 to 2, right? In fact, I should have, I don't think I can erase this anymore. Yeah, I can, there we go. I should really call that force 2 to 1, right? It's like the second number is what is actually applied to. From Canoe to 1, this is from Canoe 1 to 2. What is the original force that guy is pushing with? That's just regular old 46 newtons in the positive direction. All right, so here's Canoe 2 right here with more people in it. Okay, greater mass. And so this would be force 1 to 2. I'm going to call this, equals, that's 46 newtons. Okay, one mass, one force, one mass, one force. So that should be pretty easy, I think, to solve for the acceleration of 1 and 2. If net force, and in this case the only force on Canoe 1 equals mass of 1 times acceleration of 1, and that means acceleration is going to be the net force on 1, which is really from 2 to 1, divided by the mass of 1. So that's force 2 to 1 divided by the mass of 1. So that is negative 46 newtons divided by, what was the mass? 150 kilograms, right? Okay, so that gives me negative 0.31 meters per second squared. Not much of an acceleration, but it's a small push, and you have fairly massive canoes right there. So that's going to be the acceleration of Canoe 1. Canoe 1 is being pushed, or it's being the reaction from Canoe 2 is pushing it in the negative direction. So let's find the net acceleration on Canoe 2. All right, net force on Canoe 2 is a mass of 2 times the acceleration of 2. That's Newton's second law right there. All right, so we can say that the acceleration on Canoe 2 is a net force on Canoe 2, or the only force, divided by the mass of Canoe 2. That's force 1 applied to 2, divided by the mass of 2. And that's, of course, for the regular old 46 newtons, divided by the mass, which has more people in it, so it's going to be 250 kilograms right there. That's going to be our mass. So our acceleration that Canoe 2 is experiencing is 0.18 meters per second squared. Now look at that. for a second. Now, obviously, you probably expected that the net force on one is going to be negative, and this is going to be positive because they're going in opposite directions. But you'll notice that even though the force is the same, that is the magnitude of the force, 46 newtons applied to both, the acceleration is different. Why is this acceleration much greater, or, well, not much greater, but greater than this one right here? Well, because this is a greater mass. And so for equal forces, in order to accelerate a greater mass, you're going to have less acceleration because there's greater mass to accelerate right there. All right, so that's part A. Let me draw a line right here, and then we'll tackle part B. Oops, I'm not really drawing a line. There we go. Now you might recall that I said, well, part B, where what it asks us is, what is the separation of the canoes after 1.2 seconds of pushing? All right, well, let's draw this out real quick. So that's canoe 1 with the 2 guys in it, and this is canoe 2 right here. Okay, with more people in it, and so a force is applied from 1 to 2, and a responding force from 2 to 1. Whoops, there we go. And both of those forces are the magnitude of 46 newtons. Okay, what it's asking us is, after 1.2 seconds of pushing, what is the separation? So the question is, how far apart did canoe 1 and canoe 2 move? All right, so time equals 1.2 seconds. So here are the 2 guys right here. Here are the 3 people in canoe 2. That's 1, that's 2 right there. So if this is the center line right here where they were previously touching and they were right next to each other, the question is, how far apart did that move? All right, and how far apart did that move? So that's, run out of space here, delta x1 and delta x2. So we really want to find out how far apart they actually move. The displacement, or actually it's really just asking us what is the separation. So let's just call it the distance. All right, this would be a negative displacement right here, but we'll just think of it as the distance. That is the absolute value of this motion plus this motion. That'll give us the whole separation after 1.2 seconds. Okay. Well, we have a time. All right, and the time is 1.2 seconds. We also have some other things that aren't explicitly stated, but that we do probably know. The initial velocity. What is the initial velocity of 1? What is the initial velocity of 2? Well, there's 0, right? 0 meters per second, 0 meters per second, because the canoes were previously at rest. We know the acceleration of 1, right? That's negative 0.31 meters per second squared, and an acceleration of 2, since it has more mass, it's going to be less of an acceleration, a negative 1.8 meters per second squared. And initial velocity, acceleration, and the time. Time for both of these is 1.2 seconds. So time. All right. So can we solve for our displacement? Can we solve for displacement of 2 and displacement for 1? We sure can, because we have our equation. Displacement equals initial velocity times time plus 1/2 acceleration times time squared, right? That's our kind of our utility kinematics equation. So we're going to use that to solve for displacement of 1 and for 2. Well, the good news is that this part right here goes away because the initial velocity for both is 2. So let's just solve for displacement of 1 and 2. Okay, so let's solve for the displacement of 1 and displacement of 2. Add them together, or add their absolute values together, and then we'll get our total separation of the 2 canoes. All right, so for canoe 1, I'm not really organizing this very well, am I? Well, for canoe, delta x of canoe 1, that is 1/2 acceleration of 1 times time squared, right? So that's going to be 1/2. What's the acceleration of canoe 1? Negative 0.31 meters per second squared. I'm not going to write the units in. Times the time, which is 1.2 seconds, that squared. All right, that's going to give us our separation of canoe 1 after 1.2 seconds. 0.5 times negative 0.31 times 1.2 squared. It's 0.22 meters. Now, it should be negative 0.22 meters, but I'm just, I'll put a negative in there, and then I'll put an absolute value sign, because we're just finding the total separation. You might say the distance. All right? Delta x2, man, I'm going to run out of space here, is the same equation, 1/2 acceleration of 2 times the time squared. So that's 1/2 times, what's acceleration of 2? Oh, it's less, right, because there's more people in it. 0.18 meters per second squared times the time, 1.2 seconds, that squared. So that gives us a displacement for Canoe 2 of 0.13 meters. All right, so it hasn't moved as far, and that should make sense. In fact, I'm just going to continue this absolute value box and just make a dotted line box around it right there, all right? And that makes sense because even though the force is the same, the mass is greater with Canoe 2, and so there's less acceleration, so it doesn't go as far. So that makes sense. So we have these two displacements, or really these two distances here. Let's just add them up, and I'm just going to cheat and write it above right here. So what's 0.22 plus 0.13? That's, I think, 0.35, right? So total distance equals 0.35 meters. There we go. After 1.2 seconds of pushing. That's what I get, and this is the way that we do it. So this is Newton's third law, the action-reaction. For every force, there is an equal and opposite force. So the equal in magnitude, opposite in direction. So we notate these as force 1 on object 2 and force 2 on object 1. So hope that's helpful to you. Please make sure you ask me if you have any questions. I'll be glad to go over these with you. And thanks for watching in the meantime. I'll see you on the next one.